Welcome everyone. So you know me already. I don't need to introduce myself so extensively. Hope you're ready for the first talk of the day. Michael already said the title to you. It is rendering what matters when it matters. So this is about yet another virtualization technique. Let's first give some numbers where this context is coming from, like where this idea of the whole concept is coming from. Like most of your traffic that goes to your applications, if you build something public facing, is coming from mobile devices. And this is not something that I just made up in my mind. We can talk about some facts. So in Austria, this is about 45% of the whole traffic in the internet is caused by mobile devices. 45%, I said most, that's not true, but let's take a look at how it looks like globally. On global level, we have 65% of the whole internet traffic running through mobile devices. And if we take a look at completely different market situation, for example in India, we have it up to 80%. So especially in those regions where anyway devices are not so capable and not so strong, we have even more traffic from mobile. And that is something you always have to consider when you build international public-facing applications. Let's take a look at how those devices perform in general by taking a look at how they perform in terms of core web vitals. And we can see here that only around 30 to 40% of mobile devices manage to have good core web vitals overall. And this is kind of bad. That means like every second user has a poor experience on the web, according to core web vitals, which are not even so strict. We can also show this in bar charts. So this is in particular INP. So we see here in 2024, only 43% of all mobile devices manage to have good INP. What does it mean? More than half of your users suffer from slow responsiveness of your app while using them. Why is this, or one of the reasons why this is the case is, most of the time when you have mobile apps on the web, you build also a desktop app with the same code base. And you have just some responsiveness going on that switches the layout when whatever device size you're just going to the app. So on the right side you see the desktop application, on the left side you see the mobile application. So what is going on here under the hood is that all the components that are rendered on desktop are just finding a different place on your mobile viewport. And most of them are not even visible to the users, right? So you render them, you bootstrap them, there are ongoing subscriptions in them, they consume memory, they do DOM updates, they do whatever, but they're not even visible. Still, you render them. And that, by the end of the day, causes for a lot of mobile applications, in general, too much DOM, too many components, too much JavaScript is being executed at one given point in time. This is one example of one of our client apps. It's a sports betting app, I think. They have a lot of carousels, as you can see. And only the red part is what the user actually sees. Everything else that is marked in blue here is what the user cannot see. Yet it's there, yet you render it, yet you generate the DOM for it, and yet you have all those subscriptions going on and animations that are not even visible for the user, right? He has to first scroll to that. And too much DOM hurts really on all ends when it's coming to performance. Meaning, when we talk about the browser render pipeline, which consists of those 5 stages, there are a couple of sub-stages in between, but those are the main ones. You have scripting. Of course, too many components affect scripting. You have a lot of DOM. This causes high recalculate style phase. Also, you have a lot of DOM and complex DOM structures that you don't even need, causes heavy layouting phase. Then the browser also have to paint. You have a lot of maybe images that need to be rendered or colored borders or so. They need to be painted. And then you have those carousels going on. They need to be composited on, and the layers need to be put on top of it. So this is the browser render pipeline. And too much DOM, too many components affect each and every stage of it. And can we measure that? Because I can tell you whatever, and you have to believe me, but can we put that into numbers? Can we extract some metrics that give us an idea about what we are talking here? And yes, we can, in different ways. Let's talk first about memory usage, because of course more components, more DOM at one given point in time means that your device needs to store more things right now in memory. You can use, for example, the performance monitor, which gives you an idea of how many DOM nodes are currently in memory, how big is the JavaScript heap size at a given point in time. And in the majority of times, you can just halfen it, or even more, if you just render what's needed and not just put everything on the screen. Then we have loading speed, which is mostly communicated or measured by the metric LCP, which is one of the core web vitals. In order to have a good core web vital score, and this is still questionable if this really feels good, you need to render the biggest part of your app within 2.5 seconds, which for our experience, 2.5 seconds is not even fast. LCP is divided into 4 stages. We have time to first byte, so how long does it take to receive the first byte from the server we do a network request. Then we have resource load delay, so this means when do we start downloading the actual resource that will be our LCP element, for example, the image that we want to display. Then we have resource load time, how long does it take to download that resource in general. And then we have element render delay, meaning what other work do we have first to process in order to display our largest contentful paint. And too much DOM mostly affects the element render delay phase, because this is the stuff that has to be first executed in order to paint anything. And if this is bloated, then you delay your LCP by that. Then we can also measure that in interaction speed. This is what I said earlier about responsiveness. Interaction speed or responsiveness is typically measured in INP, which means interaction to next paint. In order to have a good score here, it means 200 milliseconds. So this kind of says how snappy does your app render a new frame after you interacted with something. You press a button and then you expect a modal popping up, or you press a button and you expect some animation to fire off. So how long is the time span between that? This is also measured in subparts, and for INP we have 3 of those. We have the input delay, so how long does it take to so that the browser can react to what you actually do. So if your main thread is currently bloated with other work, the user clicks within that time or does something, then the browser has high input delay because it cannot react immediately. It has to wait for other work to finish. Then we have the processing time, which is the actual work that you triggered, that you need in order to render something on the screen. And lastly, you have the presentation delay, so everything that has to do with rendering and painting. So if you have a lot of DOM, this stage will most likely increase. But in general, you can say too much DOM, too many components affect mostly processing time and mostly presentation time. Those are the things where we can improve. Then we have a new thing that is called soft navigations. So yeah, this is initial navigation. You know that already. You go to a web page. You enter the address into the address bar, and then you wait. You see a loading spinner, splash screen, and then all of a sudden your content appears. And then you have your LCP. In this case, it's that thing here. We can imagine this is an image, and this is just LCP. But then we are working with Angular, right? And Angular has a router, so you do not have hard navigations anymore. So there's no upcoming LCP event. You have it only once. You download the app, display it wherever the user lands. This will be LCP. When you switch a route, there is no new metric for it. So there's something missing. But we could, in theory, really need this metric, because this would explain to us how long do we have to wait until a soft navigation happens, right? We switch a route and we want to know what is the LCP for the next page. So how fast does the user perceive switching a route within your app? There is this concept of soft navigations. As I said, this is currently in experimental phase. You can enable that as a flag. There is a blog post on web.dev, I think. So yeah, you go to Chrome flags and you enable experimental web platform features, and then you are able to also measure soft LCP. And this will hopefully become at one point part of the core web vitals, because the amount of JavaScript-based web apps is kind of increasing, and that would be a really helpful metric to have. There's a talk I want to mention from my colleague Chris, who talks about exactly that topic, how to speed up soft navigations and turn them into instant navigations instead. And yeah, there's this general guideline if we talk about too much DOM. Whatever you create, this is another metric that you can keep in your mind, whatever you create, you also have to destroy. So think about soft navigations. You have one page with so many components, and you navigate back from that route. What you have to do, you have to first destroy all of those so many components in order to create the new ones. So if you create a lot, you also have to destroy a lot. What does it mean? You see on top, this is the navigation to a page with a lot of DOM, and we can see already there's a lot of work going on, very long task, and then you navigate back from this page again, and then you see here all of those nodes that you earlier created, or all of those components that you earlier created, also need to be destroyed. So you, by having a lot of DOM on your page, you also mess up the navigation to the next site because of your current situation and not of the future situation where you maybe also have a lot of DOM. So just keep that in mind. And for that, I have prepared a live demo. Quick introduction into our demo application here. Let me zoom in a bit that you also see the navigation. So yeah, I am right now at a blank page because we want to mimic the navigation from nothing to something with a lot of DOM. So I go here to native, and here you see a grid of movie cards. Yeah, this is just a very long list of movies. This is also like with CSS grid, just adjusting to the viewport size, so just so you have an idea of what this demo application is about. It just shows movie tiles in that case, and we can see here, if we inspect the DOM, that we render a lot of movie cards here. But in theory, that's the whole idea behind it. We only need the first 2 or 3 or 4 cards, because those are the only ones that are really visible. So let's see what that means for a user and measure the performance when it comes to this navigation. So I'm opening the performance panel, and before I get going, I'm throttling my CPU down a bit because I want to at least have a better picture how slower devices than the newest MacBook Pro behaves, because this is also a misconception for many people. It works fast on my machine. Yeah, of course, you're sitting in front of a MacBook and not in front of a 10-year-old smartphone, right? So let's make use of the throttling to mimic that a bit and measure the navigation to that page. We can take a look now at what is the outcome. And what we are seeing as a first measure here, INP 700 something milliseconds, which is insanely huge. It's also marked in red. Red is always dangerous. And if you remember, INP turns into red, like the worst score that you can have, above 500 milliseconds. And we can see here what causes this extremely high INP, so responsiveness. We see here this animation frame is being fired, and it has to render all of those movie cards. We see a movie card template, movie card template, movie card template. So this is our code that is being executed, and we have to render, like, I think 200 cards or so here. Yeah, and that just causes a lot of work. Of course, also when we navigate back. With that, what I could also show is the performance monitor, which is accessible from down here as a tool. And here you see the performance monitor, and here we can see JavaScript heap size, amount, and amount of DOM nodes. So if we go back to the other side, and hopefully I don't have any memory leak. Yes, okay. Just click the garbage collection, and now heap size dropped to 9 megabyte, DOM nodes 94, event listeners only 94. Let's go back to the other page. And we see all of a sudden we have 90 megabytes of JavaScript heap size and 30,000 DOM nodes. And this is not even an example that is way too huge or so. This is kind of reality for enterprisey, public-facing, big JavaScript apps. So let's go back now that we have an overview. What is the current problem? I think I can leave the throttling on for now. And yeah, just to prove my theory that forgot to show that. Just to prove the theory that this hurts on all ends, because we only took a look at scripting. Scripting is everything that is yellow here. We see here the click event and the animation frame that causes change detection afterwards and rendering all of our components. But we also see style recalculation 80 milliseconds, layout 33 milliseconds, and 80 milliseconds now seems to be not so big of a deal, but if we remember, 80 milliseconds is kind of half of the good score you need for good INP. So this is actually a lot. 80 milliseconds doesn't sound much, but if you only spend this for style recalculation, then that's kind of dangerous already. And here we also see the committing phase and the paint, of course. So all of the stages are really affected by having too many components. And just having it displayed again as the browser render pipeline, so all of the stages are right now affected and currently performing bad. And yeah, I think I don't need to say so many words about myself again, but hey, I'm Julian. I tried to solve exactly this problem today for you that I just showed you. As Michael already mentioned, working for Pushbase as an engineering manager. Yeah, in general, very interested in improving web performance, architecting with Angular, and using NX for productivity and scaling applications. So the first topic that maybe comes to your mind is, yeah, okay, let's use virtual scrolling. Virtual scrolling is a great idea. Just to onboard everyone, what virtual scrolling really means is, this is the concept of really rendering only the stuff that you currently have in your viewport. And this is a great concept. You just define a viewport that just moves across the page while the user scrolls. You have a runway that should be sized in a correct size, like how many items you have. You render 100 items, so your runway should be as large as 100 items, otherwise scrolling gets difficult. Yeah, and whenever the user scrolls, you recalculate what items you need and just display them and hide the other ones. That's kind of the concept behind virtual scrolling. There are multiple different concepts, like implementation details. One is faster than the other. The first approach that I've shown you is moving around a container and just position that container. The other approach would be to just really go item by item and absolutely position all the items properly according to the current scroll position. And I can guarantee you this works in terms of improving INP. This is a very well-proven concept. However, this works only for pure list implementations. Like everything that looks like this, just a list. It can be vertically a list or a horizontal list or a mixed match of both. It is possible, but it would not work for a grid-like scenario that I've shown you earlier. That's why I've also chosen that demo. So everything that starts with being just a for loop iterating over items and then you have just a list of items is fine. You probably could use virtual scrolling for that as long as it's list-like. And yeah, as said already, there are multiple solutions. There's the CDK package one, which is probably the most popular one. We maintain an open source project that is called RxAngular, and we have our own implementation going on that is competing with the CDK one in terms of performance. There's also a talk I want to mention that I gave 2 years ago at NG Poland about virtual scrolling in detail. So if you're interested in that, I will share the link to the slides by the end, so you don't need to learn the link by heart. And yeah, what about all the other implementations that you might have, like grids or dashboard implementations, everything that the user could customize himself, or everything that is widget layout? Or you have just a white label app, right? So you produce white label code and then people in content management systems can put whatever content they want essentially in your app. You have no for loop that you can iterate over. You have no list-like structure. They can look like whatever. What kind of techniques can we use for that? Because this is missing out. So let's just quickly demonstrate how virtual scrolling kinda works performance-wise, but kinda breaks the layout on the other end. So again, going to my demo application and just going here to virtual scrolling. And as you can see, the layout like doesn't work really anymore. I think I can scroll around, but it also looks kind of weird. Everything is jumping around. And this is, by the way, the CDK implementation. I tried to just use CDK virtual scrolling on this grid implementation that I had earlier with CSS Grid. It's simply not possible because it's not meant to be able to understand that items switch rows, can be 3 items in a row or only 2. So that's why it doesn't work, but we can measure at least if it does something in terms of performance. So let's start a new trace, move over to here, and I could already tell how much snappier that felt, and we can also see it by the number here, 69 milliseconds. And here we can see it kind of fixes all of our problems. All of a sudden, what earlier was, and if we take a look at the overview here, I see it really clearly, that is the same task than this one here. Just rendering this one single or 2 components that are visible makes such a clear difference in terms of performance or responsiveness, which is kind of crazy. But this technique is not working for our current use case. So we have to move on. But we can recap, it pretty much works and it pretty much fixes all of our issues. Scripting is less, rendering is less, painting is less, and compositing is also less. But in order to make it work for our use case, we kind of need to be more versatile. There's also a thing that is called CSS virtual scrolling. That's, I think, a term that Michael used to coin. This is not an official term, but it kind of works like that. I'm not sure if you ever heard about the CSS containment spec, but there's one specific rule that is called content visibility. And it has one value that you can give it, and that is auto. And what does auto mean? Content visibility auto means whenever you put that on a DOM node, internally what the browser does, it kind of puts an intersection observer on top of it, and whenever it's not part of the current visible viewport, it skips the whole rendering of that DOM node. So this is kind of what we really want to achieve. It has also other benefits. Outside paintings are protected to this node, and layouts from outside are also protected from this node. However, it comes with a downside. This is the downside here. When you just apply content visibility auto to a DOM node, the browser has no idea what to do with that node when it's not visible. It will just collapse to 0 if you do not specify any dimensions up front. You have to tell it how much space it should preserve while not being visible. Otherwise, the browser skips it, it collapses entirely, and the users cannot scroll anymore. For this, there's also a solution, and there comes a second rule. This is called contain intrinsic size. And that's what you also can specify with auto. This is a kind of a new feature. I think it got stable this year or last year. I'm not quite sure, but quite recent. You can either specify pixel values. You can tell it, okay, as long as this DOM node is not visible, make it just a default size of 100 pixel in width and 100 pixel in height. Or you can give it the keyword auto, which kind of means the browser tries to memorize the element last time it was visible to the user. So you scroll to it, the browser knows, okay, this DOM node has this size right now, it disappears, so I just keep the last size possible. And this is how you can mitigate the problem that everything collapses to 0 height, as long as it was visible once. Otherwise you can specify auto and a fallback value. That would be the perfect way to go here in order to use CSS virtual scrolling. Yeah, there's a talk from Michael about CSS rendering performance in general with a YouTube link here. He also gave a talk this year on the PerfNow conference specifically about CSS containment spec, if you're interested in that. And let's take a look at how this one performs compared to our JavaScript-based virtual scrolling solution from before. So this time we will again go and perform a navigation. Just real quick check that everything looks like it should look. So the grid implementation still works, definitely, that's what we can tell. Let's take a look at what content visibility actually does, because the browser will tell us. So first of all, we can see here now the styles that are applied: content visibility auto, contain intrinsic size auto, and a fallback size of 400 pixels. So it just assumes right now that every DOM node that is not visible has 400 pixels in height, so that the scroll bar is still functioning. That's what we did confirm, by the way. It does work. Probably if we really inspect that, it will be a bit jittery when we scroll down for the first time. So you will clearly notice that. Second of all, let's select an element that is not right now in the viewport. And now you can see, okay, it's cut off here in the corner, and I cannot bring it up top. But what it says here down there is descendants are skipped due to content visibility. So also the DevTools, the element panel, will tell you about content visibility is right now applied, and this DOM node will not be rendered. It will be excluded from the rendering step. So let's take a look what it means, because we clearly see movie cards are part here. So Angular code was executed, it's just the browser stuff that was improved. So let's go ahead and record another profile of this navigation. Go to CSS virtual scrolling, and we go back and we see we have an INP around 600 something. I think the first one was around 800, yes, 760. So it is a bit better. But exactly what we kind of knew before would happen. So all the Angular code, all the construction of the components here, movie card component template, all of those movie cards that we rendered are still executed. However, where we have a clear difference now is in style recalculations. This is now only 8 milliseconds and not what we had earlier was about 80 milliseconds. So if your struggle in any of your apps is you have high recalculate style phases, for example, you open a pop-up for a login screen and that takes forever because you first have to adjust some DOM styles and it has like 200 milliseconds style recalculations, then this CSS rule can be a real game changer if this is your only bottleneck. So really keep that in mind. It kind of works as it promises. It skips the rendering, so layouting and style recalculation whenever a DOM node is not visible to the user, just automatically. And I think that's such an amazing feature because it's literally 2 lines of CSS that does that for you. And it's not the first time that we have improved performance massively for a couple of clients just by applying a couple of CSS rules in their style sheet, which is pretty cool. Let's go back to the blank page. So yeah, as a recap of that, it works, it does what it should, but it doesn't affect scripting. And most of the time when we are working with Angular framework, scripting is also involved because we have to generate and construct components and render the and execute template functions and so. So yeah, let's recap what we have so far in total. Initial state, everything was bad. Then we used JavaScript virtual scrolling techniques, and it really works well when it comes to performance. We could also prove that while measuring that, but we cannot apply this everywhere. It's not versatile enough. And then we have CSS virtual scrolling, which is really helpful and can be a game changer at times. However, this doesn't fix if we have scripting issues. So there's something missing that fixes everything and is universally applicable, like CSS virtual scrolling. So what we kind of want to have is everything that CSS virtual scrolling does and just put a little bit of JavaScript on top of it and make our own solution and build it into Angular and then reuse it. So I think it's time to really do exactly that and solve the problem once and for all. And yeah, the first goal that we need to achieve is rendering when something is visible and don't render something when it's invisible. So just as a visual representation of our app, we render only the part that is visible to our user in the viewport, and everything else we just skip. However, this is super easy to implement. We have intersection observer, just a native browser API, right? We can just put it onto an element and then the browser will tell us, is this element right now visible or is it not visible? And it pushes us this information. So we can say, whenever our element is intersecting, so visible to the user, create. Whenever it's not intersecting, so it's not visible, destroy. Simple. When we just do that, we end up in a situation where the user cannot scroll anymore because we killed everything that is not visible. So there's nothing the browser would render, the scroll bar would just not be there, we cannot scroll. So with that alone, we would break the app. So next task, we want to keep the scroll intact, right? So what we kind of need is something to fill up this space, but not with our actual components, because we know already this is too much. We don't want them. So this is where the concept of placeholders come into play. So essentially what the CSS virtual scrolling does, it kind of just assumes there is a node, but there's not really a node, and we just need some replacement node in that case, and we call it placeholder. So whenever we are intersecting, we destroy the placeholder and create our actual component. Whenever we are not intersecting, we create our placeholder and destroy our actual component. So far, so simple. And if we managed to have the perfectly sized and defined placeholders that act exactly like our regular components, our job would be done here and everything would be perfect. In reality, placeholders might not have the same markup, might have different style rules, might have elements missing that define their dimensions and so. So yeah, the scroll situation would be also a bit different. So this is what we want to replace with placeholders, but we end up having placeholders that are poorly defined. Yeah, when that happens, you have a bad scroll experience. Especially if you scroll like up and down very often and the placeholders do not adjust, because then you have a constant scroll jittering experience, and your users would be like, is like, okay, it's fast, but it doesn't look good. So yeah, the next task would be keeping the scroll smooth. And what we can do with that, for that, is maintaining dimensions. So kind of the contain intrinsic size auto feature now. So we just introduce another function that is called maintain dimensions. We have a new observer that comes also from the browser spec, which is the resize observer. We attach a resize observer to our DOM node or to our placeholder, and we just get the information, how big are you right now, and we can maintain those sizes. So all in all, this would be the whole implementation. While we are intersecting, we destroy the placeholder, we reset our dimensions, we create our actual DOM node, and listen to the dimension changes again. When we're not intersecting, we are destroying our component, we are creating the placeholder, and we give it the dimensions that we have stored earlier from the visible node. And by the end of the day, hopefully everything runs fine and you get a really, really smooth and nice behaving appearance. And now we want to make it universally applicable, and that is the easiest task of all of them, because we are living in the Angular universe. In the Angular universe, we have a directive, and we put all the logic into a directive, apply it wherever we want on the DOM, and live happily ever after. So we just put a little bit of CSS containment on top of that, a little bit of view caching maybe, a little bit of concurrent mode, and we end up having what we call Rx Virtual View, which is available on RxAngular. And I want to showcase how this implementation of ours looks like in the wild. So again, first of all, we do the navigation. We check if the scrolling experience is all right. It looks kind of valid for the given moment. Let's check what it does when we scroll. So maybe I'm just make this bigger a bit and zoom in so that everyone sees everything here, because that is kind of important now. So I'm selecting the movie card here. So this element that is visible, and what I'm going to do now is I'm just scrolling a bit below and make it fall out of the viewport. Now the movie card was replaced by its placeholder, as you can tell. Whenever this appears, it just gets replaced by its placeholder, which is just a simplified version of that component, just a simple div that kind of mimics the real DOM node. So now we can go back and measure the actual performance of that thing. Throttling still enabled, run the profile, go here to virtual view, stop it, and we see here an INP of 53. Let's zoom in here. And we can clearly tell here's the click event that caused this navigation. Here's the change detection event, which is only 10 milliseconds long now, because now we only need to render one view. And all of the rest are just placeholders that are just filling up space as simple divs. So this is how we saved a lot of INP. We still have our layout in place. Everything runs quite smoothly. Still, our grid is in place. The scroll functionality is given, and one thing that we could double check here is the performance monitor. So just remember, I hope no memory leak in place. Yeah, no memory leak, cool. So this is the starting point. We have 94 DOM nodes. Then we go to native. We have 30k DOM nodes. We go back to blank, kill the memory. Again, DOM nodes are gone. We go to virtual view, and we see it's improved times 10, right? So before we had 30k, now we have 3.8 something. And this is even a real world improvement. After we have built that, we used it in the client app, the layer screenshot that I showed very early in the beginning, and we dropped from 50k down to 12k DOM nodes or so, which massively improved performance overall of the whole application. And yeah, this is the final conclusion here. We have now Rx Virtual View, which kind of solves all of our problems and is universally applicable if tweaked correctly and set up correctly. It has a big API surface. The docs are also linked here. A couple of words to mention that on top of only virtualizing nodes, we also built in RxAngular's concurrent mode. So in case you didn't hear about that, I also gave a talk specifically about this behavior, which kind of makes sure to not render so much at a given time, but rather split up the rendering into smaller chunks so the browser gets room to breathe in between and further improving performance. Yeah, this is just a shout out to our open source library that we are maintaining, where you find all the directives and all the tool sets. Please give us a star on GitHub. You can install what you have seen right now just by npm install RxAngular template. And there you will find the virtual scrolling, the virtual view, and also a competitor for the for loop. And yeah, it's time to say just shortly goodbye. I will be back on stage later at the day, but thank you so much for your time. Thanks for listening. I hope you learned something new.